Hey, well, let me begin with a little bit of housekeeping here again and say, all right, where are we and where are we headed? I think you know this, but I want to make it clear. The test is not as listed on the schedule. It's not in 2 days, but it is a week and 2 days. So we decided to do next Thursday, which we decided was May 2nd, if I remember the calendar right. And so the goal here is to do as much optics as we can. We're almost done with 37, and then we'll get into 38. So before today's over, we'll be starting with 38. And simply put, I'm just going to keep talking and do as much optics as we can until Thursday. And then wherever we get at the end of Thursday, we're going to truncate it. Because, well, like I said, we're a little behind. And even when we truncate it on Thursday, that'll put us a day behind. And so I think that's the best way to do it, and then just see, this is how far we'll get. So we'll see on Thursday how far we get, and then that's what your test will cover the following Thursday. And so when we come back a week from today, on Tuesday, as I said, we'll get started with the next unit. We'll start our modern physics, which is special relativity. It's the chapter 39, and so we shift gears yet again and get into our fourth and last unit for the semester, and then we'll just go with modern physics as far as we can until we end. And that's normal in the sense that we never expect to do all the modern physics unit. This whole last part, this last half test is just how far can we get into modern physics, how much can we get you exposed to so that you'll be that much more acquainted with it when and if your education takes you to that on the next step when you transfer from here. Because as you'll see, the next unit is very, very science-y and very little engineering-y, if there's such a word, right? And so those of you who go into the sciences will see a lot more of this, and those of you who go into the engineering, depending on what engineering, but most likely you will see very little of it in the future. So in that sense, it's good both ways. It's good to get those who you're exposed to it who won't get a chance to see it ever again and get a little bit of feel for it, and those of you who are going to get into it, get you a little bit of heads up and familiarity with it before you get hit real hard with it on a junior level. Yeah. So
Will they use relativity for GPS?
Well, and that's why I said very little. And so GPS, absolutely. Designing atom smashers, absolutely. Designing any of, not the modern day screens like this one that's an LCD, but any of the cathode ray tubes, definitely. But that's really about it. Yeah. So if you're building a car, no. If you're building an airplane, no. If you're building a space shuttle, no. If you're building an iPad, a computer, no. Yeah.
Has Don decided which date he'll do the review on?
Oh, he did. And usually he puts that on the board. And I meant to ask him myself. But good point. I am pretty sure he said Sunday. He said Sunday seems to work best for people. So count on that. Do you want me to ask him real quick, or can we wait until Thursday? Oh. Hey, Don.
It is a little bigger in the hall around.
Hey, what day are you going to do the review? Sunday?
Yeah, Sunday,
Okay.
1 to 4.
Thank you. All right, yeah, Sunday 1 to 4. All right, yeah, good point here. All right, so simply put, we've got optics today, optics on Thursday, then you got the MC on Friday, you've got also the review on Sunday. Next Tuesday, we will start with special relativity, and then we will have our test. And then when we come back from the test, we will keep going with the modern physics one. All right, well, last couple things in this chapter. As I mentioned, the simple answer to this chapter is interference. Look at the two beams, how they come together. And so we spent the majority of this chapter looking at the double slit and then variations of that. So if you recall from last Thursday, we did the double slit. Then we talked about, well, what if it's underwater? What if it's multiple colors? What if there's a lens in front? Blah, 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 blah. What if there's a mirror laid down? That was Lloyd's mirror and Lloyd's double slit. But let's look at a couple of other examples. The two big ones here are thin films, and the other one is what's called the Michelson Interferometer. In fact, it's the lab you do tomorrow or Thursday, depending on which day you have the lab here. And they're all involving an interference. As the name implies, thin film is something like this. What if I were to take, and for simplicity, let me take the absolutely perfect parallel surface, which, as you'll see when I actually show you the equipment, they won't be perfectly parallel, so we'll have to talk about that imperfections. And let me just talk about perfect one wavelength of light, monochromatic light, which again, as you'll see, you don't normally get that. We'll get as close as we can and then show you some things more realistic here. But what if I just had a thin film? And let's just say, for the sake of conversation, it's a piece of glass. But this could be glass, this could be oil, this could be water, this could be a whole slew of things. But I'm just going to take, like I said, this thin film. And let me just say it was holding it in space here, that is, in the air. So I got this piece of glass, it's really thin, I'm holding it up, it's got air on one side, it's got air on the other, and then a light beam shines on it. And so I put some light on it. And as you can see, I've got this yellow light set up to show you. I will put yellow light on our contraption here in just a second. But I'm going to shine some light on here. And as you could expect, the beam's going to come down here. And let me start right there. When it hits this first interface between the air and the glass, what will happen? Part of it is going to get reflected, and part of it is going to get transmitted. Fair enough? Now let's keep watching that beam. The beam that continues on is now going to go and hit this interface as it goes from glass into the air. Well, what's going to happen there? Exactly. Same idea. Some of it is going to reflect, and some of it is going to transmit. The two beams that I'm focusing on is, look what happens next. This beam that was once one beam has now been divided into two beams. The reason why is we got a reflection coming in and a reflection going out. You could argue that this pattern continues, and we will, because you would get at that point not only a transmitted beam, but also a reflected beam. That reflected beam would come back, and some of it would get transmitted, and some of it would get reflected. But again, we would have two beams coming out here. In fact, you can begin to see it's not going to be two beams, it's going to be an infinite number of beams. Let me just try to keep the figure as simple as possible to say, let's not worry about all these other beams. Because if we can understand what happens with these two, we will also see it happens with the third, the fourth, the fifth, the sixth. So let's study these two beams. Because here's my question. If somebody was standing up here, looking at the light that is reflecting off of this thin film, this coating, this could be oil on water, okay? This could be, as my glass is, a small silicon film that they put on the surface of the glass. What is this person, as they look into this thin film, going to see? And so, as we did so many times before, well, the light here, as it comes together, may combine constructively or destructively, or kind of in between. So just like we did for the double slit, let's run through the same type of analysis. Let's look at it and say, well, what would happen, or what are the conditions needed for those two beams to add up constructively, for them to be in phase, for this person here to see bright or maximum light reflection? Well, again, just like we saw with the double slit, you would have to study the extra path difference, right? And with this path difference, down and back is one wavelength, or two wavelengths, or three wavelengths. You get the idea. Wouldn't these two beams then be in phase? And so let me write that on the board here first. What if I had an integer number of wavelengths, where m is either a 1 or a 2 or a 3 or a 4. I guess it could even be 0, I suppose, meaning really we have no thickness to it. That's kind of a trivial answer, if you will. But 1 wavelength, 2 wavelengths, 3 wavelengths. You would expect then to get bright maximums, right? Now, that number of wavelengths has to fit where? Now, if we say that the thin film has a thickness of T, then I would say this. Although I'm not quite done, there's 2 more things I really have to add to this, which is actually the hardest part. I think these are the easy steps. This is what it's saying. This is saying if the down and back, and I should probably pause here, I've kind of overly simplified it. I've drawn it at a slight angle so you could see it, but I'm thinking of the light really straight down and straight up. Kind of the simplest case. Now, same kind of thing can happen. We would just have to come in at an angle, and so this would be 2t divided by the sine or cosine of the angle, depending on which angle you would have to use here. So we could change this a little bit and do a little trigonometry. We won't even go that far. There's just other things we want you to see, so I think that'll make sense. And like I said, those of you who go into optics beyond this class, you probably will do off of directly down and directly back up. But I just want to emphasize what I'm doing. The simplest case is straight down and straight up. So this picture here doesn't really do it justice. I've drawn it at an angle so you can see the multiple reflections. But here's really what I'm looking at. I'm looking at the beam coming pretty much straight in and then straight back. And so the 2 beams are kind of on top of each other, and the person then making the observation is straight up. All right, so keeping it as simple as I can, that's the extra distance that this second ray travels down and back. The thickness is T, it's 2T. And if that's an integer number of wavelengths, I would expect constructive, except I really should modify this a little bit. Wavelength where? In the film, right? And so again, going back to chapter 35, I better add this extra piece here, that it's not just how many wavelengths, it's how many wavelengths in that medium where the second beam is. And this is the second beam. So the second beam is in this glass. So in this little diagram, this would be 1.5. I'll write it as an N to indicate that we may not be in 1.5. This could be a film of oil or a film of water, but I'd have to use whatever index that light is in. The other tough thing is, remember, I'm not using the index above and below, I'm using the index of the film itself.
When it goes into the film, is it going straight through like you drew it there? Like a straight line doesn't sort of...
Yeah, I've drawn it at an angle.
Because you know when we it doesn't diffract, like it should refract.
Oh, right. Now, if we go straight down like this, there is no Snell's law, or there is no refraction. I guess there's still Snell's law, and Snell's law says it doesn't bend at all. So if you went straight down, there'd be no bending, and it would just do that picture. And that's really what I'm doing. So that's why I'm not worried about the angle of incidence, theta 1, the angle of refraction, theta 2, and I'm kind of ignoring that effect because it doesn't happen when I go straight down. You can see that it does happen if you're at an angle. And you can see then the geometry is much harder if you're at an angle. And so that's why we just kind of do straight down this semester, and next semester, if you have a next semester in optics, we'll do at an angle.
The way you've drawn this, wouldn't it be the darkest spots?
So there's 2 things that I want you to catch. I've done this, which is the wavelength in there, and there's one other little subtlety that I am missing in this picture. What am I missing? Right. And so the added piece to this is what I would have expected to be maximums, because the path length is 2, except Here's the added piece. What happens right here when the light goes from air to glass? What did we say when something hits something more dense? Yeah, we did it last time with Lloyd's mirror, and we brought it up from back in chapter 18, and I'm going to put a red circle around it to say right here there is a phase change. When that light reflects, if it was pointing up, it was a crest when it hit. When it reflects, there's an inversion there. How about this one though? How about this reflection? All right, this is hitting something less dense than that. So no red circle here. So the last piece, and I think the most difficult piece to get, is right here. This is not bright as we might have first expected, based upon a path difference being an integer number of wavelengths. But it is actually, as you pointed out, dark, and we would get very little light reflection. We would be under a destructive interference. So I'll say it again, because in order for this thin film to make sense, you've got to include not only the extra path difference, but also the extra phase shift. And so my mental approach is this. I like to look at the path difference. If the path difference is an integer number of wavelength, my first thought is that would have been, and still could be, constructive interference if nothing else happens. But if one of them, so in other words, based on path difference, the one is pointing up, crest, the other is pointing up, crest, but if one of them goes under a phase change and the other one doesn't, then I get destructive interference. And so I like to write this out and say, well, this is the equation I kind of expected. I kind of expected this to be bright, but because one underwent a phase change, it's actually dark. Fair enough? Which then would modify this equation to the other half of this. How would I get bright, or maximum, or constructive interference for this reflection? What would condition have to be true?
Why is it the phase change? Why does the phase change occur when it reflects off there?
Oh, I should have brought that machine out again. Do you remember the machine? Well, way back in chapter 18 I did it, but didn't I bring it out recently too? Yeah, that little rod machine, and I made the little hump and it went down, and when that end is clamped, when you hit something hard, the rods were going up, and when you hit something hard, this rod tried to go up, but because it was clamped, it wouldn't let it. So as this rod tried to pull up, Newton's third law says the reaction force is this rod will then pull this one down. So it pulls up, because it doesn't go anywhere, and then so this one pulls down. And you could imagine that if I was on this end pulling down, I would make a hump that would go down. So a hump that is pointing up and hit something solid, the reaction force, Newton's third law, is to pull it down. And so the hump goes downward. And so you get an inversion when you hit something really hard, something solid. And so what we're saying here, the same thing happens in optics, that when you hit something more solid, which in this case from air to the glass, the higher index, you're going to get a phase change. But if you hit something less solid, you don't. So we don't get a phase change here, and we do there. And so that's why this, which I would have thought would have been bright because it's an integer number of wavelengths, now because of that one undergoes a phase change, it now becomes dark. And so the opposite is true here. If I were to write this on the board, I would have said if the thickness, or twice the thickness, that's the extra path difference. If the extra path difference is an integer and a half wavelengths, 1, 2, 1.5, 2.5, 3.5, 4.5, I would have expected the two beams to have destructive interference. That is, one is pointing up and the other is pointing down. But because one of them underwent a phase change, now they're aligned again, and you get constructive. So this becomes my equation for constructive. This becomes my equation for destructive. Here's a warning for you. Work it out each time. Because this same equation could be switched with bright and dark depending on how many phase changes and depending on other situations. And so this is one of these examples where I have said many times there's some cases where you can plug and chug and be fine and do okay, get an okay grade, you know, transfer to an okay school, have an okay career with okay salary, an okay spouse with okay kids, right? But there's other ones, and this is a big one, where you can't just get away. You got to analyze this every single time, because watch the next step. Notice I put this word reflection here. Let's say the person is standing on the other side and is looking now at the transmitted light. Well, according to this equation, I am getting destructive interference for the reflected. Another way of saying that is there is very little light going back. So where is the light? It's going through. The whole reason it is dark on reflection is because it is bright on transmission. So this same equation that told me where to find dark spots is also the same equation which is telling me where to find the bright or the constructive interference if I'm looking at the transmitted light. And that's why I was saying, don't just memorize this equation and say, oh, this is the equation that gives me dark. Oh no. This is the equation that gives you dark for reflection. But it gives you maximums for transmitted. Same thing can be said here. If I look then at the transmitted light over here, this same equation would give me dark. And very little light would get transmitted through the thin film in this case. A lot of it gets reflected. So again, same equation, but you have to be careful what's being asked or what do you want in your engineering problem. If you want to get a lot of light reflected, then this is the condition you want. You want then to design the piece of glass with a certain thickness based on a certain wavelength so that you will get a lot of light on reflection. And if you do that, you won't get much on transmission. I mean, the two quick examples that come to my mind is it's these thin coatings that they put on glasses or they put on solar cells that can really make a difference in the efficiency, because if you want to get a lot of light transmitted through, put a thin film on it so that very little light gets reflected, meaning most of it goes through. And so you'll put your silicon wafer here in your solar cell. You'll place a small thin film on top of it, although the indexes are different, so we're going to have to talk about this. This is not the best example yet to talk about a thin film. But the point is that thin film will help get more light through. More light gets through than would have otherwise if you didn't have that. And my glasses are even coated that same way. I don't even know if you... Okay. It's probably so small you can see, but there's a small coating on it that if I take the light off of here, they've designed it so that it'll get as much light through to my eyes. You know, if this was a camera lens, the most I can get through to the camera, because I want my eyes to detect the most light, right? Also, in this case, don't want it to reflect, and you know, you get that reflection of your glasses, and people don't like that. But so on a glasses, it's more aesthetics. On a camera or camera, it's more of just get more light into it. But I can see it on mine because you got to realize you got to design this for a certain wavelength. So since the whole spectrum, you know, everything from the reds on one side to the blues on the other side, they usually design it right in the middle, in the greens. And so in my case, what would happen is if I put it under white light, almost no green will reflect. And so sure enough, when I look at this white light and I look at the reflection on my glasses, I can see kind of a magenta, meaning I'm getting a little bit of red reflect, I'm getting a little bit of blue reflect, but almost no green reflect. Well, yeah, a bunch of questions.
What about, so because this phase shift reverses because it's a hard reflection. So what about a thin layer? If you have a thin layer of water on glass, because that way the third layer would be a higher medium than the middle one, and therefore both will be hard reflections.
Exactly. So here's my next step for you. This is why I was saying you don't want to just kind of memorize and plug and chug into this equation, because notice that this equation reversed roles between reflection and transmission. Fair enough? This equation reversed roles between transmission and reflection. Let me do it again. Maybe to make it a little clearer, let me do it in blue here. I come over here with the blue one and I say, all right, now let's change the index. And there's all kinds of combinations you can have. Your suggestion was put a little bit of water, so N, on a piece of glass, and I'm going to assume you meant air on the outside. All right, so the light comes from the air, strikes the water, gets a first reflection there, goes a little bit deeper, hits then the glass, and reflects off the glass, and those are the two beams I would talk about. So, let's come over here and look at reflection. Thinking of this blue situation on reflection, if twice the thickness was an integer number of wavelengths, by itself I would have expected constructive interference. Fair enough? But now let's look at the phase changes. And again, using the red for the phase change, let me ask you, is there a phase change on this first reflection from air to the water? Yeah, so I'll circle it in red. Is there a phase change from the water into the glass? Yes. So I'll circle it in red. So, back to here, I would have expected by itself, if twice the thickness is an integer number of wavelengths, one wave would be up, the other wave would be up. But now, one goes under a phase, but so does the other. So aren't they still constructive? So it's kind of like neither one went under a phase change. Now, the truth is both of them did. But I would have expected this equation then to give me a bright reflection, maximums. And sure enough, I would use this equation for maximums on reflection instead of dark on reflection. See how important it is to pay attention to whether or not you have either one or two or no phase changes, because this equation can change roles. First, this equation was an equation that gave me dark on reflection and bright on transmission. Now all of a sudden, because I have a different scenario, it's the same equation that now gives me bright on reflection. And since it gives me bright on reflection, it's going to give me dark on transmission. And so it all depends on how many phase changes I have, as well as the thickness of the film. Yeah.
Are we just getting the phase shift at the reflected ray or the transmitted ray?
Oh, yeah, okay, good. Keep in mind, again, maybe I'll have to go back. Maybe I really should have brought that machine. But in chapter 18, okay, we made the little wave, and we had the long rods, and then I connected it to the small rods. And I'll just tell you the result from that. Is sometimes we got a phase change on reflection, and sometimes we didn't. And the argument was you get a phase change when you hit something more dense. Now, that wasn't your question. Your question was about transmission. Great question. We never had a phase change on transmission, regardless. So none of this discussion, did I mention anything about this part right here where the light is coming out. When it comes out, or these parts where it comes out, there is no phase change there. So there's only a phase change on reflection. And even that is only sometimes do you have a phase change on reflection. So again, keep that in mind. Never a phase change on transmission, and only sometimes on reflection.
So is there any way to have the same on both sides with the brighter, darker?
No, no, because if one's taking the energy from the other, right? Otherwise, you'd violate conservation of energy, right? Which would be a good problem to have. So we would solve our energy problems in an instant like that. But nature doesn't allow us to do that, so no. And you can do it by also counting the number of phase changes here. I did not actually do that, but if we come back to this one, if you look closely at it, the one that goes all the way through is transmitted. No phase changes, right? The one that actually comes out here to also interferes, reflected here, both had a phase change. And so it would be as if no phase change. So what you will always see is the one that is reflected will have one of the rays will have one more phase change than the other. And the one that transmits will have an even number, I guess is what I'm looking for. Either 2 phase changes or 4 phase changes or 6 phase changes. Whereas this, if you add up the number of phase changes, on reflection comes out to be 1 or 3 or 5, an odd number. So that way you will always get one side constructive and the other side destructive. They may switch roles, but you're always going to get one side constructive and one side destructive. And of course, if you didn't have that, you would have maybe constructive or destructive on both sides. Either one, you would be either creating or losing energy, and we couldn't have that.
So the bright side will never be as bright as the original beam, right?
Right?
Because some of the light had to go through the other side and eventually got canceled.
Well, if I truly got destructive, then this would be as bright as the original beam. If I could get everything perfect.
That light has to go through to the other side, and it doesn't get canceled until the other beam gets to it. So how does the energy get back to the original beam?
How do I answer that? Maybe the thing to answer is just because the beam went this way, okay, doesn't necessarily mean it has any energy, which sounds weird. But isn't its energy related to its amplitude squared? So if I could say this, I would say that this beam that goes through here, that is dark on transmitted, is quote unquote a beam that doesn't have to go this way and then go back. What happens is it is a total beam of 0 amplitude. So there's no energy with it. And I don't know if that's a better answer than going back from away from the wave model back to the particle model and say, well, they just don't go this way. They all ricochet off. Huh? How what?
One-way windows. One-way windows.
Oh! They could work that way. Yes, yes. But really what you're talking about is these, now they usually make them a little more sophisticated than this. But if you take a thin film on top of a thin film on top of a thin film on top of a thin film, what they call dielectric stack, in the optics, this could be extremely accurate. That, the amount of light reflected is almost 100%. Far better than you would get with a mirror. And so many of your high quality optics do not use mirrors, but they use dielectric stacks of thin films. And you're tuning up a laser, you can get far better reflection. Because a mirror, even a bathroom mirror is about, 80, 85, 90% reflection. A good polished front lens mirror, actually it's kind of scary to look in. People look at it, just throws you off. It's so bright. We should show you one in lab. We've got one. And you just kind of look at it and you just go, oh, it's kind of eerie. You get like, you get like 97% of the light reflected, and it just doesn't feel right. You're so used to it being dulled a little bit on reflection. But that's still 97, 98, 99. Okay. Which 99 sounds good, but even 99% reflection can hurt you in a good optical equipment because you're ricocheting around thousands of times. So 99% raised to a power of 1,000 can really diminish your energy very quickly. So you need to get really, really close to 100%. And so this is how you get 100%. You take the multiple reflections. And so this cancels with this, 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 cancels with this. And you truly get almost nothing this way and 100% that way. Well, back to my discussion, because I wanted to warn you about this equation. Notice that so far what we've seen, and there's a bunch of possibilities that we haven't even seen yet, but this equation could have been used to represent dark on reflection or bright on transmission, or it could have been used to represent bright on reflection or dark on transmission. And so that one equation fits all those four combinations there. And I need to figure out which one is valid for that case, and the best way to do that is to come back and look at your indexes of refraction there. Okay? And so, keeping with the blue, I should, I guess, continue this. Because right here, if we look at the reflected light here, if this equation was giving me bright on reflection, then this equation should be giving me the dark, or the minimum. And again, you can kind of see that, because this is saying that if twice the thickness, the path difference down and back, is 1.5 wavelengths, or 2.5 wavelengths, or 3.5 wavelengths, or 4.5 wavelengths, I would expect destructive interference. But that wouldn't be the end of the story. I'd have to look at the phase changes. But they both undergo a phase change. So it doesn't really affect the overall outcome. And so there is my answer for reflection. Whereas then that means if the thickness is just right, the transmitted light would be for the bright one. And it would be for your maximums. Okay. So again, you got to kind of pause and ask yourself, what situation do I have? Do I have a situation like this where the top one undergoes a phase change and the other ones don't? Or this situation where they both undergo a phase change? And you can imagine that this continues. I'll run out of colors and possibilities. I'll go ahead and use red, but I was kind of reserving red to point out the phase changes. That's all the colors we have today? Bummer. Well, and I am. Because I think that's the hardest thing, is the phase change. So I'm going to save my red for that. But look at another scenario. Let me clean this up here. We could have done something else. What if the reverse of this, say, was true? What if the light was already in the glass and trying to come out of the glass, and as it tried to come out of the glass, there was a thin set of, well, I'll just do water for a moment, on the surface as we tried to go into the air. And again, as I analyze that, I would say one beam would come down and hit the surface and reflect. The other one would hit the next surface and reflect. And of course, there would also be all these other multiple beams, but really all I got to do is study one scenario, and I think I know the other four combinations. And in this case, I would look at this and say, are there any phase changes? Because my first reaction is to say, if twice the thickness is an integer number of wavelengths, that would be bright. But I can't stop there. I got to ask myself, are there any phase changes? And so, getting my red pen, is there a phase change as it goes from the glass and reflects off the water boundary? No. So, no red circle. Is there a phase change when it goes from the water boundary into the air? No. So, no red circle. And so there's no phase changes here. So this original equation, the twice the thickness equals an integer number of wavelengths, that I thought would give me bright does give me bright on reflection. It continues to give me bright. There's no added effect that, oh, one switched and the other one didn't. Which is why I decided to draw this scenario in blue, because this same equation, blue, would apply. That equation applies to the blue applies to that equation, the blue applies to that equation. And it could be something else. And it will happen to fit the green pattern, so I'll go to the green. Yeah.
When you're inside the water, when it reflects off the air and then comes back and reflects off the glass, is there phase change there?
Oh, yes. Now, if you want me to continue to draw this, I will. Okay. And so there would be a reflection here, and which would go that way, which would give a reflection there, which would give a reflection there. Okay. And you're right that there would be a phase change for this beam coming out right there. But I would argue then that also, if I said this right, that, wait, yeah, there's a phase change here. This one is not. Okay? So if I look at the transmitted light, the transmitted light would have one phase change.
So you only need to look at the first one and determine that.
Yeah, I think the best approach is to look at these two reflected beams and to find out if it is bright or dark, and then the transmit is going to be the opposite. Right. Yeah. And let me try a fourth combination before I show you some of the experiments, and then you can see there's all kinds of combinations that can come up, and you just have to stop and analyze it. But another combination could have easily been that the light started in the glass and had an oily film on top. And then that oily film went into another piece of glass. Or, well, no, I didn't say that well. Two pieces of glass with an oil film between them. So I got a piece of glass, a little oil sandwiched between there, right? And so if I look at that, I would say this one bounces off, and this one bounces off. And of course other things happen, but let's just look at these two, because once I got those two, I can really have everything else. And then I'll pull out the red marker again and say, is there a phase shift on the reflection between the glass into the oil? No. How about from the oil off this other glass surface? Yeah. So I will put a red circle there, indicating that that would be a phase shift. So that one beam has a phase shift and the other one doesn't. That's why this scenario is almost identical to this scenario. It's just here the top beam went under the reflection and the bottom one didn't. Here the bottom one does and the top one doesn't. But either way, when I wrote out my equation that said an integer number of wavelengths equals to twice the thickness, I would have said that my first reaction is to say that that would give me bright. And so I'd kind of hold my fingers up. Integer number of wavelengths. But I'd have to realize that this lower one went under a phase change. And so I got destructive. And so what I thought was going to be bright based upon just the path difference now becomes dark because of one went under a phase change. And so this would be my equation to represent dark on reflection. So it would also be my equation to represent bright on transmission. And then, of course, when the half wavelength, they would reverse roles. And so that's my green scenario. So the end result is only two different type of combinations. But how you get to there can be a lot of different combinations. It's why I decided to kind of set this up and maybe show you kind of the real thing. And I just realized that now that I set it all up, I kind of put everything in front of it. That's not good. So maybe I'll move things out of the way here a little bit, and then I'll have to realign it when we get that far here. But if you can see from your vantage point, I don't want to mess with this, I have some light. This is the sodium light we've been using in the lab. This is our yellow sodium one, and what's going to happen here is this puts out a wavelength of about 589 nanometers, almost one frequency. It's got actually two really close together there, but it's almost a single frequency. And that single frequency is kind of nice to show you this illustration, because I have taken this. I have taken a piece of glass, two pieces of glass. And for those of you who might be able to be close enough to see it, I have a piece of glass. It's pretty thick. And I have just dropped another piece of glass right on top of it. Just plop. There it is. Yeah.
Can you project what you're showing us to that camera?
I can. I'm glad you say that because that's just about what I'm going to do. But I kind of wanted to hold a second because you're also going to see the end result here. But this is the first piece of glass, and I just dropped a second piece of glass on top of it. Now that second piece of glass will probably come to rest on a piece of dust. Chances are the pieces of dust will be maybe like that. So it wouldn't surprise me if it, is not touching the edge or anything, right? And chances are I don't think those two pieces of dust are the same size. So I'm going to take advantage of the fact that it's probably got some dust on there, but here's what I want you to see. I have an air pocket between those two pieces of glass. Index 1.
Are they both the same? Are the glasses both the same index?
I'll say yes to that. I'm not really sure. Doesn't matter, no. They just need to be larger than 1, exactly. And so I have a scenario that looks like this, where I have high and small in the middle, which means they would be undergoing one phase change down here on the bottom, which would mean they would fit our green pattern that we have up here. That means that when the thickness, or twice the thickness, is an integer number of wavelengths, and be careful with n, in this case, which is n? 1, right? It's where the light is in the thin film, so that would be a 1. But what I would get is if the thickness is an integer number of wavelengths, I would get very little light reflected. But when the light, I erased it, is an integer and a half wavelengths, I would get a lot of light reflected depending on the thickness. And the scenario I gave you was the simple case, an exactly even uniform thickness. I can't get that. What I can get is a wedge shape, and the thickness changes. And that's what you're going to see up here. Yeah.
So the wavelength, that's the wavelength in a vacuum?
Well, we usually label in our equations the wavelength in a vacuum.
Okay.
So then that's why in our equations we have a lambda divided by an n, meaning because when we actually do the experiment, we want to know the wavelength where. But when we talk about wavelength, like so we can all be clear, and since the wavelength changes in a different medium, when I say, what is the wavelength of that sodium light, and I say 589 nanometers, I mean, that's what it would be in a vacuum. When it goes into the glass, it's going to be a little different, of course. Yeah.
So if air wasn't involved in this, would it be like N1 over N2?
Well, no, this is the extra path length, and so I would want to use the n for wherever the wavelength is, or the material, the beam is, that is having the interference. So I would say that it's this n that I care about. It has nothing to do with this or this. It is that just once these beams, because at the start the beams are in the same medium. And then once this second beam comes into here, they're in the same medium. So the difference is what I care about. The difference is all occurring in this thickness here. And so I care how thick is it, and in thickness compared to how many wavelengths do I have in that medium. And so in my setup, the n would be 1. In this picture that we talked about, I had some oil between them. And so the index would be 1.2. But what I wanted you to see is what would you expect then, given this, and then looking at this picture, to see when you have something that is a little more complicated, something that is a wedge shape. Well, let's see. As we already said, at certain thicknesses, I would expect to get dark. But at other thicknesses, I would expect to get bright. And so as I look into here, what I would expect is there would be some thicknesses that would be twice the thickness would be an integer number of wavelengths. Maybe I'll write it this way up above. I like to say at some thicknesses, there'll be an integer number of half wavelengths. So simply put, if this piece of dust is small, then this thickness right here may actually be a half wavelength of light. Right? And if it is, that means the beam that comes in and bounces here and then goes through there and bounces again, the beam that goes into this little air pocket travels a half down and a half back. It travels one wavelength further. And that's what this would mean. One wavelength further when it goes down and back. And because one undergoes a phase change and the other one doesn't, this extra thickness of a half wavelength would then have destructive interference, and right here, as I look into here, would look like a dark place wherever it had a thickness of a half a wavelength. But on the other hand, as I move over slightly away from there, the thickness gets a little bit more. And let's say the thickness becomes 3/4 of a wavelength thick. If it's 3/4 of a wavelength thick, that means down and back is 1.5 wavelengths. And with that extra phase change, they would mean they are constructive, and then I would get bright. And so as I look down, I would expect to see adjacent to areas that are dark, areas that are bright. And in this wedge shape, I would expect to see the thickness constantly changing, and so I would have a place where I get destructive, constructive, destructive, constructive, destructive, constructive. And that is what I'm hoping you can see here. Can you see constructive, destructive, constructive, destructive, constructive, destructive? This little piece, if I may, touch it. I will change the thickness between them.
If we shine white light on it, will we get a rainbow?
Ah, good. Next good question. See, because right now, we started with single wavelength, single thickness. Now I got a wedge. Now, let's do multiple colors. But, there it is. In fact, maybe I'll even change the whole dust pattern by just picking it up, dropping it again. Oops. There we go.
It's smaller or like more.
And see how they're packed in tight together compared to last time? What does that tell you?
The wedge is a little
more flat.
A little more flat or a little more wedged? And as you'll see when you do the homework, this is one of your questions. They give you a picture, then you guys are supposed to count them, and you're supposed to say how thick is the wedge. See, because every time we go from a bright to bright or dark to dark, one more fringe, right? The thickness then is growing by a half a wavelength. So if you see a lot of fringe lines, that tells you it's pretty thick, right? Yeah, and so this scenario, if this is what I had before I dropped it, now I probably have something like that, right? I got a much bigger thickness. And I can count the number of fringes. And I can figure out then bright, dark, bright, dark, bright, dark. And if I get to number 33, then I can put into my equation here and tell you how thick is it at the end of that wedge. Oh, yeah, a bunch of questions, yeah.
So I'm a little confused because we label like one of these bright max, one of these dark, but if it's dependent on like t, like the distance, how do we know it's bright if we don't even know t, like the distance between the two plates?
Well, I guess that's the scenario I'm giving you. The scenario I'm giving you now is, let's say we know the wavelength. We can use that to find t.
So we're saying like we see a bright dark.
Right.
They tell you in the question, okay, it's
Right.
you get
As opposed to, and then that's what I'm showing you now, as opposed to what we discussed earlier. Earlier I discussed, all right, if I give you a thickness, and that's what, you know, the engineers are, I guess, doing with my glasses. They're saying, okay, how thick do we need to make it? Well, that's, I guess, a still thickness question. But they go, how thick do we need to make it so that we can maximize the light in the green? Yeah.
Okay, so from that picture, since it's a wedge, the thickness isn't the same all the way throughout.
Right, which is why you go from bright, dark. Because if it was all the same thickness, it would either be, a whole thing would be bright, or dark, or somewhere in between. Remember that this is not like the thickness has to be an exact number, but according to this equation, when this is an exact integer, there is an exact thickness that you will get dark. And there's many thicknesses that you will get dark.
That's different. If you count a certain amount over, you can calculate the thickness at that spot.
Yes.
Okay.
Right. So what I would do is come over here. I mean, well, maybe we should even do it here. This is our equation. We're looking on reflection. This is the equation that gives us dark. So let's focus on the dark ones. The thing is, I don't know if this end actually touches or if both are sitting on a dust piece. But for the sake of discussion, let's just say it is actually touching. So I know that the height there is 0. And so 0 would be, right, a thickness of 0 at m equals 0 does match this equation. I should get a dark right where they touch. And that kind of makes sense, because right where they touch, one would be going under a phase and the other wouldn't, but there'd be no path distance. So they'd be at a phase, and I should get destructive and a dark one. So one end of my wedge should be dark, okay? And so that kind of looks like there's a dark one right there. And so maybe that's the edge that's touching. So then I would say that would where m equals to 0 in that equation. And so m equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and my picture could be better, but let's say it's 18. I could then come in here and say, all right, I have the 18th dark fringe right on the far edge. I put m equal to 18, I put n equal to 1, I put wavelength 589 nanometers, I get the thickness of this end of the wedge. And to illustrate it, let me push on it. Because if this is a piece of dust, if I push on it, I'll probably smash that piece of dust. And my wedge should be a little bit less. And I should get less bright dark spots across here. And so I'll come in here and say, all right, what about it?
That's one piece of dust. You moved it.
All right. So I changed it a little bit there, and you can kind of see. Probably just added dust instead of took it away. Yeah, so there's a little bit less. But if I could smash it all the way. Yeah. But see now, if I start at dark, 1, 2, 3, 4, 5, 6-ish. 6. So I'd put m equal to 6 in here, and I have a much smaller thickness now between them. But hopefully you're also seeing the beauty of the optics. You can really measure some real accuracy. And so those of you who think, don't I need to worry about it, I'm not going into optics. Sorry, you mechanical people are going to care about this. They're great measuring instruments here. How do we get the difference between them? And the next one is, what if this was then multicolored light?
Rainbow.
Right, what you hopefully see is that there would be a solution of the thickness for a certain color. Let's say red, right? In fact, I'll change my scenario here to maybe this scenario. The green, well, I guess it's this scenario. It still fits the same equation of green, but it won't be hard to make this one. I can have air on the outside, then I can have, well, this says glass, but I'll use water and soap. And this will be my thin film, and then this will be my index on the other side. And if I take then some soap, soap. And fill up a ring, and maybe use the room lights in here. If you look on the end of a bubble, can you see the reflection of the lights? Very, very little?
So that's not dispersion?
No, it's thin film. And so if you've ever seen a soap bubble, or another good scenario is oil on water, and so, you know, out on a rainy day, as soon as it rains, because there is so much oil on the ground, and if you look at those bubbles, or if you look at the light, you will hopefully see different colors, because there would be different thicknesses as the soap is kind of migrating around here. And if I just maybe even leave it in the ring and, I don't know, and angle it, is there a certain, can you guys kind of see a rainbow effect?
Yes.
And you'll see where it is blue, and you'll see a rainbow pattern, right? You'll see it go from red, orange, yellow, green, blue, and then start over again. Red, orange, yellow, green, blue. Because again, you're getting that thin film and that interference for them. And of course, if it's really thin, that's where you can see red stand out from blue. I'll pass these around. These are kind of nice to see too. This is just, you know, two pieces of window glass just laid on top of each other. But if you just hold it up here and look at it, and you know, here's the light, look at it, you will see the pattern, the reds and the greens, and you'll see a rainbow. And the nice thing about it is just kind of squish it, because you'll see like a contour. And so just like you probably learned in your math class about contour lines, if you follow a red line, and so in my case, I'm looking at, well, that green one's standing out. I'll do that green one. But that green one goes like this and around like this. What do I know about that contour line? It's always the same thickness, right? And if I jump over to the next green one, then I know that that's a half a wavelength thicker or thinner. I don't know which way it goes. But I know that the thickness of the next green one is a half a wavelength. And so I could go through, and every green one maps out a contour level, a place where between these two glass it has a certain thickness. So that's kind of our homemade one. This one works pretty good too, so I'll send this one around. These are our professional bought ones. But look at it and press on it. These have thumb screws that you can tighten. Although maybe, I'm not sure if we should tighten them, because Don centered them up really good. And he got them, he tried to make kind of a cone shape. It looks more elliptical shape, but he's got these contour lines. And yes, and it was covered by Newton. So we call these Newton's rings, yes. Yeah. And so, oh, he got this one adjusted really well. These are nice, these are almost perfect circles. This is more elliptical. Yeah.
Shouldn't the bubbles have dark spots, dark lines between the rainbow effect?
Well, okay, but because you have all the different colors, okay, there would be, so let me leave this on the board. This is the equation for the thickness that gave us dark on reflection. The other equation, and so I'll put dark and then bright. The other equation is the solution for the thicknesses that give us bright on reflection, okay? And yes, there are many places that you would be getting dark, but if you're getting dark, you don't notice you're getting dark, because for that same thickness, there's a different wavelength that you're getting bright. And so in other words, when I see a green contour line, that means I have matched this condition for green light. And maybe the red is being destructive at that point, which is why I see the green so much better. Because if I had constructive for all the colors at one time, I would just see white light reflected. And so I get a green mostly. The other ones are off of there, and so the other ones are either completely destructive or less constructive, that the green stands out to me, and I see mostly green. And so one dominates it. But all the way, when you have all those wavelengths, that's why it's a little harder to understand and a little harder to see, because you've got all the wavelengths with all the different thicknesses. There's all kinds of combinations you can get. Yeah.
So if you had contour lines that were not perfectly straight, wouldn't the one with the smaller radius have to be a smaller thickness?
Smaller radius.
If you were pressing on the glass,
Yeah.
and you had contour lines,
Yeah.
the one with the smaller radius would have to be closer to the part that was pressed. And so you would know that that would be a smaller thickness because it had a smaller radius of the contour line.
Oh, right, exactly, and that's my point here. The shape and pattern and thickness and color of these contour lines can give us so much information about the thickness of things that are microscopically small. So when we're manufacturing things in our electronical world, we gotta optically analyze it. Yeah. Years ago, I was able to go on a neat tour down at TRW, who was building the next generation telescope to replace the Hubble telescope. In fact, they're still working on it. It's been a slow process, but that's an interesting story in itself. But it was interesting talking with the mechanical people, because they were really trying to get the things to move and the optics to move, and that was their job. And so I was going on the tour, and they were answering the question, how are they measuring all of these very things? And one of the mechanical engineers said, "Oh, we've got to learn so much new optics." He just rolled his eyes, and I just thought that was funny. And I go, "No, really, how are you doing it?" And he goes, "Really, we're doing a interferometer." I think they were using a Perot interferometer. I'm about to show you another interferometer, but you'll see the idea. That's the lab this week. But they were using the interference of the light, kind of like these thin films. And they were measuring, distances to 40 nanometers. So yeah, we got to get this accurate down to 40 nanometers. That's why we need to relearn our optics, so that we can make our mechanics and our moving parts. We want to be able to move at, within plus or minus 40 nanometers to get the telescope to work. It's like, pretty clever. Yeah. Of course, they were also doing it at 40 Kelvin, which made it also another challenge too, because that's going to be the operational temperature when this thing goes up. Well, anyways, I hope you got that idea. Let's go to another step here. Look at this. Here's the equipment you guys will be doing in the lab this week. This is called a Michelson Interferometer. And again, it's the same basic idea. You are going to send the laser beam in here. It'll hit what I call a partial reflecting mirror here and split the beam into two. Then one beam will come over to this mirror and the other beam will go to that mirror. They will bounce back, hit the partially reflecting mirror, rejoin, and get projected on this screen. Well, what will you see? Well, let's talk about this here for a moment. Let me draw a picture. And like I said, it makes a good one for the lab, because we've got well, not a bunch of these, but a few. We're going to have to put you guys in big groups. And we're going to have to reflect them. Are the mirrors perfect? Not 100%. Well, the first mirror is a 50% mirror. Right. The other mirrors are the best we can get with polished silver. So they're like 99% reflection. Yeah. And so let me do this here. Let me just draw a picture and say, okay, here's my laser beam. Here's my light source. Let it come in and hit my mirror. Now I will call this a 50% mirror, meaning that it hits this surface and half of it goes this way and half of it goes through. Now, of course, what's going to make it real hard on your alignment and on your eyes tomorrow in class is that once you also have reflections off of this surface and bouncing around, and so we want to ignore that. But, of course, in reality, it's there, and so as you run the experiment and you adjust things, you're going to have to figure out which is the part that I want, which is the part I don't want. And you're going to have to adjust this within a fraction of the wavelength of light. Okay? And so it is a very, very small accuracy, but fortunately the equipment is made so that can be done. Okay. Then on this end I will put a mirror. Let me call it a 100% mirror, although as you pointed out it's going to be a 100% mirror. Let me put a mirror over here, also another mirror, 100% mirror, because here's the idea that this first beam reflecting off the 50% mirror then hits the 100% mirror, then comes down and goes through this 50% mirror, which of course means 50% more of it goes that way. So by this time we're down to 25%, but not worrying about this beam. This is the one I want to focus on. Same thing can be said about this beam. This beam's going to come in. Whoops, already drew coming in. Bouncing off. Unfortunately, it's going to reflect here. That's going to be probably the most annoying piece of the experiment because you really want to ignore that one. And it's not very far from what you do want to focus on, which is that one. But at this point, this is 50%. Unfortunately, that's a lot more than this. This is only somewhere down around a 10% reflection. So you can tell a difference between them. But if I put a screen down here, and hopefully don't pay any attention to that, what am I going to see right here?
Right.
Well, it depends how much further that leg is than that leg, right? And so, what if one leg is an integer number of wavelengths further than the other?
Dark or bright?
All right, fair enough. You're getting to the point that you will see bright or dark. The next part is we got to look at the phase changes, right? And so let's look at the phase changes. Don't they both undergo a phase change when they hit that mirror? All right. So I'll circle them in red, but since they both undergo it, and we're really interested in the difference between them, I'll ignore it from here on out. Okay? The real question is right here, as this one comes in and bounces off of this mirror, doesn't this one undergo a phase change when it goes that way? All right. So that beam does, and of course then it transmits through, so then it doesn't have any phase change. The other beam goes through, bounces, okay, we already talked about that phase change, and then the only other bouncing it does is right here, that reflection. Phase change or not?
It does. Wait, no, it does not because
It's actually in the glass at this point, trying to get out of the glass into air. So no phase change.
Wouldn't it undergo a phase change entering the plasma?
It would never go under a phase change going in because it's transmitted, right? All right, so simply put, one of the beams, this one, will have one more phase change than the other one. All right, so if this leg was an integer number of wavelengths further, so I will say R number 2 minus R number 1. What I mean by that is how much further is one mirror or one beam traveling compared to the other. If that is an integer number of wavelengths, and I'll say integer in whatever index we are, but aren't we really traveling in air? Until tomorrow. And you do this underwater. No, you won't do it underwater. But you will do something else. All right, so I'm going to put an end there to keep that in mind. But it could be obviously underwater. I don't see any interest in that. But that would be it. But if that was an integer number of wavelengths, I would expect, my first reaction is that should be bright spots. But because we said those were phase changes, this then should give me a dark. And so as this comes along, I should get dark. But on the other hand, if that path difference, if one mirror being further than the other, is an integer and a half wavelengths, I would expect to get bright. Now the good news for you is you don't really need to know what the difference is. You can just look at the screen and say, all right, what am I getting right now? And so what you're going to do is hook it up and get it adjusted. That alone is going to take a while. I'll wait for the lab to do that, and you'll adjust it and you'll set it up and you'll look right there and say, okay, I have a dark spot right there. All right, well if you have a dark spot, then that means you are an integer number of wavelengths different. Maybe it's one wavelength, maybe it's two, maybe it's 1,000, maybe it's 1,000,000. Who knows? 1,000,000 would be a little too much. Our optics aren't quite that long. But it doesn't really matter. You would get a bright spot. And then one of these mirrors is movable.
So what is this? So what is projecting on the screen like flash back and forth?
So, and we have different models. And so in lab I will show you. But in this model, when you adjust this, you are moving this mirror. Ever so slightly. Okay? But you will move this mirror, and I want you to get ready for tomorrow. What will you see then happening right here as you move that mirror?
It starts flashing, it starts dimming, right?
Yeah. If it was bright, it will dim to dark and then start to go bright and go bright, dark, bright, dark, bright, dark, bright, dark, bright, dark.
So what is the energy dose?
Good question. Hang on. Well, I'll just answer it. Remember, we got the opposite over here.
Oh.
So if this is dark here, this is going to be bright. And these are going to switch roles. Just like the transmitted and reflected was with the thin film. So we don't lose any energy. So if we're getting destructive somewhere, we're getting constructive somewhere else. Guaranteed.
Are we assuming that those two beams are overlapping on the bottom?
Yes, yes. That's what makes the alignment hard, is you've got to adjust these mirrors to get these beams to overlap
I mean,
within one wavelength.
the one that are like 4 inches apart on the board?
This one?
Yeah.
No, this is one that I was saying is annoying because right, it's a reflection off here, and students have a hard time distinguishing what I want to overlap here versus that one. So I was just kind of warning you about it.
You say it was glass?
Yeah. Well, it's a polished glass with just a little bit of silver in it so that it'll reflect 50% of the light, not 99% of the light. Okay. But that is, as I said, your interferometer. It's a Michelson interferometer. It was built by Michelson, so we do a lab on it. It's also going to become real handy, believe it or not, when we do a discussion about a very famous experiment in special relativity. And so Michelson is going to use this interferometer, and so that's why I want to make sure I brought it up here. Your author gives you a good picture of a interferometer here, I think, and says, okay, how does this thing work? And so, guess we're done with this. And so, what do you see here? And so, again, you're going to, they got a telescope here. We won't need a telescope. We'll just put it on a screen because we'll have a bright laser. Actually, the first one will have a bright laser you can put on the screen. The other one, you will have to use your eye. It's so dim you'll have to use your eye. But you won't need a telescope. It's not that dim. So we'll just look right at it and get it. But the point is, if you move the mirror, how far do you have to move the mirror for this to go from bright to dark? Yeah, half a wavelength. Why? No, I'm sorry. From bright to dark, the whole. Okay, I didn't say that real well. I'll try it again. But you got it right. From bright to dark would be a half wavelength. But remember, the light beam goes out and back. So the mirror only has to move a quarter of a wavelength. If the mirror moves a quarter of a wavelength, then the increased path difference will be a half a wavelength because it have to go down and back. And that's why it will go from bright to dark. So this thing can pick up movement of a quarter of a wavelength like that. And if you're willing to accept not full bright to full dark, from bright to semi-bright, you can pick up easily the 1/10 of a wavelength of the movement of this mirror. And so that's why these interferometers can be really, really accurate here in measuring very, very small distances. It's a fraction of a wavelength, and the wavelength of light is already a fraction of a meter. And so you can get really, really small distance here with the movement of this mirror.
On the diagram there, reflected rays coming off of mirror number 2,
Yeah?
those would transmit through mirror naught
Yeah?
and would hit the light source.
Oh, okay.
So not all the light that it comes in.
Exactly. To be a little more accurate here, I would have this beam would come up, 50% of it would go this way, bounce back, and when it hit here, 50% of that, so 25% of the original would go this way and 25% would go that way. The same thing what you're talking about, mirror 2, it would go this way. When it got back to here, half of this beam would go that one, which is the one I'm going to care about. The other half would also go this way. So I would get a pattern here, but I would also get a pattern here. And that was Danny's question earlier, that if this is dark, where'd the energy go? Well, that's because this one's bright. And if this one's bright, this one's dark.
So if you look over there, what is possible to get a perfect mirror sort?
Yeah, so it could be the equivalent of, by using interference, you can get the equivalent of a perfect mirror, which was your question earlier. Yeah. Now, I need to point out one other thing that's really not shown in this diagram, and your author, I guess, decided that it was just beyond the level of this class, except you need to at least mention it because you're going to see it tomorrow in class and it can throw you off. But the good news, it's going to make your alignment a lot easier. What about just to the left or right? Let's just say, for the sake of discussion, that when I get it all hooked up, I notice that I get a bright spot in the center. And so I'm going to call this the center. It's bright. Now, of course, what that tells me is the path difference between the two beams is a half wavelength, 1.5, 2.5, 3.5, some integer and a half wavelengths. Okay? But what about just to the left? Or just to the right?
What's a longer distance?
All right. And so, without doing too much analyzing of this, let me say this. That the light that hits here is actually coming, say, from this mirror on a path that's a little bit at an angle. Fair enough? Whereas the light from this path comes here and angles from here. But see how they are angling from a different location? And my point is that the path difference for these two beams off of center isn't the same as the path difference on center. So if on center is bright, as I move either to the left or to the right, one beam gains a distance on the other. And so what's eventually going to happen when I move far enough left or far enough right? I'll get dark. And of course, in 3 dimensions, I'm going to get a ring. And so this is what you will be looking for in the lab. We call it the bullseye. Some of you will call it the target symbol, right? It'll look just like target. It will have a bright spot in the center. Then it will be dark. Then it will be bright. Then it will be dark. Then it will be bright. Then it will be bright. Then it will be dark. And fortunately, it's a good big picture that you can focus your eyes on. But all we're going to care about as we count them is the center. And so your job is to look at the center and move the mirror and go bright, 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 bright. Remember, every time it goes from bright to bright, how far does the mirror move? Half wavelength, right? Bright to dark is a quarter wavelength movement, right? Because bright to dark is a half wavelength path difference, and then half that. But bright to bright means the path difference had to change by 1 wavelength, which means the mirror had to move by a half wavelength. And this is the only time I've ever seen this in the instructions of our lab manual, where it says, by the author, count these, move the mirrors slowly, count them carefully. It's a little tricky. You may not get it right the first time. You may have to do it many times. No cursing is allowed. And that's directly what it says in the instructions there. So to tell you, it is a little, and actually that's not the real frustrating part here. But I'll mention that one. But as you're doing this, you're going to be counting. 1, 2, 3, 4, 5. Move the mirror slowly. You don't want to miss any of these, and you're going to count them. And your eyes are, you can't blink either. So we keep it at a low number. I think the instructions said go ahead and count 50. Because if you move it 50, then you know the mirror has moved 25 wavelengths. And your first part is just that, calibrating the mirror. Your whole idea is, if I move this dial 1 centimeter, how much does the mirror move? And so your whole first part is to figure out what we call the leverage arm of this thing. If this moves 1 centimeter, how much does the mirror move? And the mirror will move a small fraction of that. And you got to find out what it is. And so you do that by shining a known wavelength and calibrating it and looking at that bullseye. Yeah.
Could you explain one more time which distances are, like the difference between which distances makes the bullseye?
Yeah. I'll either redraw it or I'll try it up here. Okay. Here's the light source. Okay. And it's going to hit the mirror. So one of them is going to go what your author calls L1, and the other one's going to go L2. L1 and L2 are based on where did you place mirror number 1 and mirror number 2. So when they come back together right here and go towards you, the difference between this L2 and this L1 would be that path length. I called it R1 and R2, but to be matching that picture, I guess this would be 2L2 minus 2L1, calling L1 the distance to the mirror there. And so the difference between them, it's down and back, so that's why the 2 is in there, right? Now, the hardest part of the lab is right here. What if we take a certain area here, we got this little chamber, and we make it a vacuum. So it's got a glass window on this side and a glass window on that side. But the real thing is, it's got a vacuum in here. So if we put a vacuum in here, what's going to happen to this wavelength?
Faster?
It's going to travel faster. I'm not worried about speed. This is so fast I can never measure the speed. But there's a longer wavelength, right? And so that longer wavelength may make it change from a bright to a dark. Or may change it from a bright to another bright, because just the wavelength is longer. And my point is, if before you put this in here, if you had, say, these things exactly matched so that their path difference was 0. Once you put this in, their path difference still may be 0, but aren't you going to have more waves here than here? Because aren't the waves in this vacuum now a little bit longer? And so here's something to think about tonight and get ready for tomorrow's lab, is if I put this in and I look, and let's just say for the sake of conversation it's bright, so I get a bright spot here, then I know that if there is, a certain number of waves here and a certain number of waves here, the difference between those is an integer, so this is bright. What if I slowly let air in. What happens to the wave in here? It starts to get smaller. And this, what used to be constructive, if I let enough air in, what will happen? It'll get destructive. If I let more in, it'll go constructive again. If I let more air in, it goes destructive. And if I keep letting air in until this whole chamber fills up to atmospheric pressure, and I count these, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, doesn't that tell me how the wavelength was in the vacuum to where it is now? And if I know what the wavelength is now when I added air, wouldn't that tell me the index of air? Anybody remember what the index of air was? 1.000. Yeah, it rounds to a 3. I think it was like a 2.9. No, there's 3 zeros and then a 3. So it's 1, 000, and then a 3. Here's the neat thing about the lab, I think. You're going to measure that. You're going to get the index to 3 10,000ths. 3 parts in 10,000. And there really illustrates the value of the interference of the light. You can measure the index. Although you got to let the air in slowly. That's the part where it says don't cuss, because what happens is you'll let it in too fast the first time. Then you'll let it in too slow and nothing will happen, and then you'll keep playing with it, and eventually you'll get it right. And you got to count them. 1, 2, 3, 4, 5, 6. Wait, that was too fast. All right, try it again. 1, 2, 3. But eventually you'll get them, and you'll get the index of air. Yeah.
So I know this wouldn't change the measurement, but wouldn't the walls of the container slow the light more than the vacuum is speeding it up?
Yeah, but it has nothing to do with speed.
I mean, you said that this contraption would make the wave get there
Yeah.
faster, but I'm saying the walls would
Oh,
slow the light down
yeah.
more than the vacuum is speeding it up.
I don't know. It depends how thick my walls are.
Well, you're talking about 10,000ths of the difference between a vacuum and not a vacuum, but those walls are 1.5.
Fair enough.
You'd have to have
I'd have to have like,
a really big vacuum.
yeah, okay, fair enough. Yeah, okay. Agreed. But again, I'm not even going to pay attention to those. What I'm going to pay attention to is the difference between before I let air in and after I let air in. And in that case, the glass was already there before I let it in and after I let it in. Well, like I said, this is your diagram. In fact, let me just add to this, because one of the neat experiments is the ongoing looking for what's called gravitational waves. And so if you want to see a big interferometer, here is a very long interferometer. It's the last picture in your book, but here's their laser beam, and it goes out this arm, off that mirror, and back, and off this arm, and back. And I wish I could remember how big this number is. I think it's 1 kilometer long. I bet it's right here in the book. It says how long this interferometer is. They got 2 of them. One's up in Washington, and the other one New Mexico. But, and I think they even say in here where these are. Yeah, the laser interferometer of the Gravitational Wave Observatory, Richmond, Washington. No, they don't mention the second one. They say it's perpendicular. No, and they don't say how long it is. I think somewhere in here they do. Maybe not. Well, anyways, my point is just to point out, very useful. It can measure a small fraction of the movement of the mirror. And in case you're curious, why do they have this? Is they're trying to measure gravitational waves. And nobody's ever measured gravitational waves, but the theory is that just like we have electric fields that oscillate, we would expect gravity and space itself to oscillate. And so, if there is a movement of this mirror, a fraction of a wavelength of light, couldn't we detect it? And so if you put these 2 mirrors really far apart, and a big gravitational wave comes, it may move that mirror before it moves that mirror. And if you do, you'll pick up an interference pattern. Of course, you've got to measure this small movement, and that's why it's way out in Richmond, Washington. Unfortunately, it's so hypersensitive that they actually pick up trucks driving on this road. They pick up people walking in Seattle, mass people, not individual people, which is why you put another one in the other part of the United States. So if you, whatever you get, you know, is hopefully random in nature and a different randomness than in New Mexico. But if they agree, then that was probably a giant wave that hit the whole Earth simultaneously. So that's what they've been looking for and hoping to find, and good $100 million well spent to find nothing. I don't know. It's always the debate in science, but I think they'll get. I think they'll get it someday. I tell a question? No. No.
Did you find one yet, or?
No.
At least I know it works.
No.
2 kilometers.
It's 2 kilometers. Is that what it? You looked up? Yeah.
The laser interferometer with gravitational
Yeah.
wave observatory.
2 kilometers. Now is that down and back? So it's 1 kilometer long, or?
Half a length at 2 kilometers.
Ah. So down and back is 4 kilometers.
And the second detector is half the length at 2 kilometers.
So it works though, right? I mean, it's not wasted. We just haven't been.
Right. We haven't found them. Right. Yeah. So good. I mean, that's the whole point. Is it wasted or is it not?
Could we say that there haven't been any waves?
Probably not.
Otherwise, this would have worked, right?
No. We would say there hasn't been any waves of sufficient magnitude that this can detect.
Probably like the noise.
Because if I do this, there should be a gravitational wave, any movement of gravitational field. And so what they're hoping to pick up is strong waves that probably were generated in a supernova explosion that then traveled at the speed of light to get to us. So they're waiting to pick up that. And so, all right, well, oops, and all of that took a little bit longer than I kind of wanted to do, but that's the end of the chapter and or the beginning of the next chapter. Because your author then says, all right, let's keep looking at this. And I'm not real sure why your author does this. He kind of takes the next topic and he gets started in chapter 37 here, but he doesn't complete it till he gets into the next chapter. So I thought I would use this as an opportunity to just tie it together here. And so I'll say it this way. Why don't I say we're done with chapter 37 and I'm starting 38? Although, when you are looking at 37, you will see that your author kind of mentions multiple slits before he gets done with the chapter, but he doesn't continue the discussion till he gets into the next chapter. And I'm just going to tie it together because I think they should be together. And of course, we're short on time, so we're just going to go as far as we can here. And so as we are leaving 37 now and starting 38, and we got about a half hour left, and then we've got one more lecture on our optics, let's ask the next question. What if instead of having 2 slits, I have 3? Or instead of 3, I have 4, 5, 6, 7, 10, 600 will be my ultimate step here. But it could be any number that we want. And again, your author does a pretty good picture here to say, okay, well, let's take a look at a couple of these multiple slit diagrams here. This is probably... yeah, maybe a... well, this is the results. Yeah, I'll do the results here. But you might remember this top one, at least I hope you do. That was our long discussion that we spent the majority of this chapter on, is what happens if you have 2 slits. And maybe I'll put that way back here on the side. We did this. We started our discussion by saying, all right, if you had only 2 slits, then what we would look at is at the interference of those 2. And we said then the path difference being d sine theta, where d was the distance between the slits, and then theta is this angle up on the screen. If that is an integer number of wavelengths, we would expect to get positions where the light is really bright. And in fact, we spent a long time talking about that, and then we finished last lecture with coming up with this equation. This equation said what would be the intensity on the screen. And if you remember us getting that, we took two waves. We took wave number 1, which we wrote like this, kx minus omega t, and wave number 2, and we wrote like this, and we said, well, what do you get? What is the total of those two? Now, let me not take the time to repeat those, but let me springboard off of those and say, okay, let's extend that. Let's go from this pattern right here, where n equals 2, and what we found was this cosine squared function, to 3. All right? And so, if I just draw a dotted line, and I put some point P up here, and not shown really well in my picture, you need to remember that these 3 slits are really close together. And so if I draw from here to here to here, and I call D the distance between any adjacent slits again, so now it's a little more complicated. You know, it's, what do I mean by D? I mean adjacent slit. So from slit to slit, how far is it? But I think you can see that if you look at d sine theta, where d sine theta is the path difference between any adjacent holes, back here when we did the double slit, we said that they were constructive. If these two are adding up constructively, what would you say about the next two? Yeah, they're adding up constructively too. So if d sine theta equals an integer number of wavelengths, gave you bright positions for the double slit, it also gives you the bright positions for the triple slit. And if we go to the quadruple slit, again, if d sine theta is an integer number of wavelengths and you get constructive between any two, well, then these two would add up, but these two would add up, and these two would add up. And so again, the same condition would give you bright spots. And so that's why your author kind of starts here in the double slit and continues on into the next chapter where we get to, 600 slits, where we begin to call it a gradient. And so he talks about that and says, there's really not too much different. There are some things that are different, and that's what I want to point out. But so far there is not. In fact, you can see this in what your author calls the intensity pattern. He's trying to say, look at a double slit. This is the maximums for the double slit. What does the triple slit look like?
Same maximum point.
And what I want to point out here is you do have the same location of the maximums, whether you have 3, 4, 5, or 10, or 600. They're at the same location. So this equation, d sine theta, is kind of nice. Not only did it apply for 2 slits, but it applied for 3 or 4 or 5. Now, as you can probably see in that picture, the in-between stuff does change. So let's look a little closer at these multiple slits. But the biggest picture to point out here is the position of them. Of the multiple slits is the same. So it doesn't really matter how many slits you have. Same equation will tell you where they're bright. Yeah.
What if the D's are different?
Oh, between what?
Like from one another?
Oh, from one to another?
Yeah.
I'll start with saying well, that's beyond how far we're going to go in our optics. I'll follow that with, well, what we could do is we could then start breaking it into like a double slit here and another double slit, and then, because you got different spacing, and so you're asking, well, what would I have if I had 2 double slits on top of each other? And so I would get one pattern that looked like this, and another pattern on top of it, and where the two patterns added together I'd get constructively, and the other ones I would get semi-constructive. Does that make sense? Yeah. So we could analyze it. I don't think it's beyond the scope of our knowledge, but that's how I would do ones that the distance between the slit changes. But like I said, I'll also point it out that's for your next level of your optics class. Okay. Well, let's see if this makes any sense. I think this one, and especially these little humps in between, are kind of hard to understand. So I'm going to try this. Remember this? Remember we were adding two waves together? Let's see if I can draw a picture of that. I'm going to go 2 slits. Now, if you remember, we did it mathematically. We took wave 1, wave 2, we called this sine A plus sine B, and we did a trig identity. Let me change that and do it a little pictorially. Here's what I mean by pictorially. Let me represent this first electric field with a little arrowhead. And I'll just leave that one alone. I'm going to draw it horizontally. But what do I mean by that little arrowhead? That little arrowhead is representing the intensity of that beam. Because what I have to add to it is another little arrowhead. But this little arrowhead is out of phase with the other one. And so I will add to it a second arrowhead that is slightly out of phase. And so if these two are slightly out of phase, this then is the result of those two. If we're looking at the double slit right down the center, right here, then phi would be 0, and the two arrowheads would point in the straight line. Watch, see if this animation helps here. Here, going back to our flash animation, we should really change our home page here. College departments, academic departments, physics, web page, finally, flash physics, there we go. And so down here under the optics, we have a good picture of this. Not that one. There it is. Doesn't fit well. I wonder if, because I know, let me get a better format. All right, let's try this again. What was it? College departments, academic departments, physics, web page, flash, optics, double slit phaser. Much better. Okay, even that's a little too big. But what I want to do is start right there. And again, I don't want to necessarily do the double slit all over again. But what I want to do is, number one, give you kind of a backdoor insight to what we call phasers. It's not really the main intent here, but you are going to learn the power of phasers either by a formal lecture or informal lectures. Very powerful tools, and we do it a lot in electronics. We do it a little bit in our electromagnetics. I'm going to do it just a little bit here, but here's what I want you to see. When I added two beams together last time, I did this. I said this plus this, right? And I just did the trig identities. But a visual picture, and that's what phasers are. Phasers are a visual picture of adding two trig functions together. And so here is electric field number 1, phaser 1. Here is phaser number 2, electric field number 2. If we are looking right here down the central maximum, I could represent that as arrowhead 1 plus arrowhead 2. And so they're in red here. I got them in blue over there. The resulting is in blue here, but I got it in red there. But this, they add up constructively. We are looking at a point in the center of the screen, and we are getting bright because these two electric fields add up right in phase. But if we move a little bit off of the center of the screen, okay, we have something that hopefully looks a little bit more like this in our phasor diagram. That is, the first electric field, I won't change, I'll just leave it there. But the second one is at an angle compared to the first one. And so the resulting electric field, as you can see, is a little bit smaller. And that's what this is trying to represent. Phasor 1 plus phasor 2, the result is in blue, and this electric field, this blue line, I think you can see is smaller now than it was a moment ago. A moment ago it was as big as it will ever get here. But when I move off of the center, it gets smaller and 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 smaller, and right about there, these two waves are 90 degrees out of phase, pi over 2. And if I put that into here, I would, of course, get, cosine of 45, and I square that, I get 1/2. So I should have half the intensity. And sure enough, hopefully it's showing that the intensity has dropped to a half. Where would the half go to, where would the intensity go to 0? Exactly. So if I keep going further along the screen, when those two waves are 180 degrees out of phase, and that's the neat thing about phasors, you can kind of visually see one direction and then the other direction. And when you add them together, they cancel off, and you get no electric field, which means no intensity, and that's the dark spot. So if that made sense, when we move over to 3 slits, we could go and write out 3 waves. We could say E naught sine kx minus omega t plus E naught sine kx minus omega t plus phi plus E naught sine kx minus omega t plus 2 phi, because the next wave would be twice the phase compared to the first one. So if we call this our reference point, then this one is out of phase from it, and then this one is more out of phase compared to the first one. And you can see 4 wavelengths would really be a mess. I would have E naught sine blah blah blah, E naught sine blah blah plus phi plus E naught sine blah 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 plus 2 phi plus E naught sine blah 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 plus 3 phi. Here's my question. You want to add these together? You want to add these together? You want to add 10 of them together? It's probably better if we do it visually with phasors than if we come back and do our trig identities. So let's do it visually here. And this will hopefully explain the intensity pattern that you just saw a moment ago. And in fact, let me put that visual pattern back up here. Look carefully. What did you see for 3 slits or 4 slits compared to 2 slits? Now the first one I already showed you. Isn't the position of the maximum still the same? But what else have you noticed?
Mainly disturbances.
Yeah, what happens is between the bright spots is very useful and interesting. Between them, you can see that this 3, and more so for the 4, isn't the bright one getting narrower?
When you have nodes, you have secondary maximums or
Yeah. You also have little humps. And so notice the little humps. Here, there's 1 little hump, 2, 3, and this would be 8 little humps. Okay? And so you have little humps between them, but you also have the beam itself, the brightness, very narrow. And that's what is very nice about a phasor diagram. If I come back over here and look at then, not the double slit, but the multiple slit, here is a repeat of the phasor diagram for the double slit. Look at the 3 phasors for the triple slit. and look at the 4 phasers for the quadruple slit, if I move this along here, step, 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 step. Maybe you're beginning to see it already. What are you noticing about the multiple slits compared to the double slits?
Changes faster?
It does start to get smaller much, much faster. And that's what I meant by that narrowing in. And so your bright spots come to be very narrow, right? And so it gets real narrow. In fact, if I keep stepping this forward a little bit, step, 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 right here, where the double slit has only dropped to half the intensity, as we said before, look at the quadruple slit. What does it drop to?
Square.
That plus that plus that plus that is 0. 0 intensity. And so the more slits I have, the quicker that's going to drop to 0. The narrower this little bright spot, or this, I should say, this big bright spot is, it is really narrow. And so then, as you go along away from center, step, 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 step. Maybe I'll stop there. You'll see that the triple slit has gone to 0. The double slit hasn't gone to 0 yet. The quadruple slit already went to 0, and now it's actually starting to increase again, because a triangle would be the first 3 like this, and then the 4th one would be this. So the resultant is just buried under there, and it got a little bigger. So there's a small little intensity pattern. Probably so small you can't see with your eyes, although when I shine the laser here, you'll barely see it if we get it real dark in here. But if I keep going step by step by step, maybe there, you'll begin to see that for multiple slits, they're kind of all curled up on each other. That's why you never get it bright again until they all line up out of this. And so if I keep going here, actually there's dark again for the quadruple slit. It's also dark for the first time for the double slit. And over here with the triple slit, it kind of got a little bright again. But you can see that if we keep moving along, eventually, all of these phasers will be 360 degrees out of phase, and we're back to bright again. So they all get bright at the same spot again. But the multiple slits get much narrower. And that's probably where we'll end up with time here. I want you to see, if I take this laser beam and I shine it onto this wall here, rearrange things here again, but I'm going to put that laser on our screen over here, and here has many different slits. That says 2, 3, 4, 5, and 6. Let me start at the 2. If I shine this through 2 and power down the lights here, I think you can see bright, dark, right? Now it's going to be hard to tell that they're in the same location, but I'll just kind of slide it from 2 over to 3. Do those bright spots kind of look the same location? I'll go back to 2. So here's 2. And here's 3. So I don't know if you can really tell that there's a difference. And that's actually probably good, because that is telling me that the bright spots are in the same place. But also, and from your distance, it might be hard to tell that there, in between them, is a little bright spot. And when I'm this close, I can see it. I couldn't see it when it's that far away. But I can see a small bright one between them. But what I can see, and maybe you can begin to see at your distance, and I'll maybe have to go to 4, 5, or 6 before you really see it, is that the bright spots are getting narrower. Let me slide it over to 4 openings. Maybe now you might be able to see a little bit more. Do those bright spots look a little tighter together? No? If I go back to 2, because on the 2 they look blurry. They almost run together. But
Not the same total intensity under the curve?
yeah, yeah. And so that, well, the way they made these, probably not exactly. But there's 3. Here's 4. Here's 5. No, here's 5. And I should answer that better. No, it's not, because they're actually doing more slits, the same size. So the intensity is actually going up too.
Okay.
Yeah. And that's probably why you can see more dots left and right. Is that what you're wondering? But I think that one's a good one. Can you tell they're closer? I mean, I can see like little dark spaces in between them. Here's 6. And that's a little bit of a change. But before you go, let me do the 600. What's the 600 one going to look like? And of course, to get 600 of them, they do have to be closer together. So D is going to get closer together, which means the first order is spread out, right? And if there's 600, how many little bright spots in between do we have? 598. And bummer. I'm going to have to shoot it up a little bit. There we go. And I got it vertical. Maybe I should do it horizontal like the other ones. But there's the central one. Then there's 598 little bright ones, which you can't even see. And there's the next bright one. And then there'll be 598. And I think it's over here on the door somewhere. I don't see it. Maybe easier to find it this way. But here's the central one. There's 1. There's 2. Right? And so this is a diffraction gradient, and that's why the multiple slits are really nice. You get bright spots, and the equation is the same. That's the neat thing. And you get a big space in between that's dark, and so you just go bright, nothing, bright, almost nothing, I should say. Bright, almost nothing. All right, well, we'll call it quits there. It looks like we just got started into